So last time we talked about our CPU. Our CPU has program memory where we write instructions. It has also random access memory, which after reset has some either zeros or some old random numbers. And we also have CPU. And the CPU is actually not that complicated. It consists of uh, general purpose registers that hold some temporary values. We have arithmetic logic unit that does all the math. We also have this program counter, which cycles us through the code. And we have some inputs and outputs for accessing random access memory. Actually, basic processors contain this and not really much else. So now we will focus more on this assembly programming, the way that processor works on some larger things. So today we will do some exercises. And for example, this task 1. So in programming language, you oftentimes define some variables and then you do some operations on them. For example, here we define unsigned integer, 8-bit integer a, b, and c, and we want to add a and b together and write it to c. In reality, since all programs have many variables, variables are rarely, if not never, stored in registers. They're always stored in RAM. So if we pick some random location in our code and we do some operations with numbers, most probably they are stored in RAM. And for these operations, they are only taken from RAM to CPU. Then some calculation is performed and the result is written back to random access memory. And then CPU does other things to other numbers and so on. So anyway, always the way that CPU works on numbers is it reads them from the RAM, does the operation, and then stores to RAM. So one moment. Today we will just practice this assembly thing. So the first task is basically copy A and B from RAM into registers, then perform addition on these numbers, and then store the result into the third memory location. And these memory locations are written here. A is located at address 0. So for example, in this RAM, if I take hand tool in Logisim, in this MCU view, using hand tool, I can click on any memory location in RAM, for example, location 0, and I can write in some number, for example, 42. These numbers are in hexadecimal format. You just have to kind of remember that. So these numbers are in hex. So it's 42 is 4 times 16 plus 2. I don't know how much that is. Next number is B is located at some address, for example, address number 4. So here I will write the second number, which will be 55, and the result should be written to address number 8. So this address. So let's just calculate on the calculator in hexadecimal format. 42 plus 55 is 97. In this case, hex and decimal are the same, but okay, let's just leave this example as is, and then we will test it with different numbers later. So, okay, so first number is, for example, 42, and the second is 55. So now we need to write the assembly code and to write it into program memory. And we will be doing everything by hand, just like we did just like people did in 1970s, right? So to write assembly code, we first need the documentation of our processor. So it is put in Artus and it's called instruction set. And the first page is instructions with some explanations, with some examples, and so on. So we have this. Second sheet, which I will be using today, is just summary without much explanation, just instruction name, its operation code, and then organized in 4 bits, the locations of the parameters. So we have arithmetic logic unit operations, add with carry, increment, decrement, negate, subtract, and so on. We also have compare with carry. Next is load LDI, which is copying numbers. But in this case, we will not copy numbers because as a generic example, we'll take these values from RAM. So next is load from RAM. This is what we will use to copy numbers from RAM to registers, because CPU can only do operations on registers. It cannot do them on RAM. And then store result, and also the jump instruction. The rest of the instructions we will do in later lessons. So today, all we need to do know is load from RAM, add, and store to RAM, and jump. So let's just try to write this code. So in this case, I am using Notepad++ because it has line numbering. It's just a good feature. And in settings under preferences, in language preferences, language, or here, oh yeah, settings preferences language, I set tab size to 8 because that's how assembly was usually done. So, okay, so let's just start typing our program. The first tab space is for labels. We're not using labels, so I start writing code on the second tab stop. It's the first tab stop. So instead of starting to write at the beginning, I write with one tab ahead. You can write this code right now in a notepad, or if you're using Mac, you can use this text edit program or any word processor, basically, because you will be compiling by hand. We don't have a compiler for our CPU. We will be compiling and assembling everything by hand. So first, please write in the chat box if you have been programming anything in assembly previously. Maybe you had a subject where you did assembly programming, or maybe you did it in work or in school or something like that. So please write in the chat. So first person says that Jocelyn has never written anything in assembly. So everybody else also just type in, have you written anything in assembly or not? Okay, so almost nobody has written anything on assembly. That makes a double responsibility on me, because if I teach you wrong, you'll, you'll think about assembly in the wrong manner for the rest of your life. So in assembly language, we just write instructions as provided in instruction set. So for example, we want to copy some value from RAM address to our variable, and we have been given the address name. So I just write LDR, which means load from RAM. And in different assembly languages, it's called differently. There are some assembly languages where it's called just LD. But in our case, it will be LDR. So after one tab stop, I write the operands, and the first one is the register into which I want to copy the value. So for example, from address number 0, I want to copy to register number R0. Then I give the address from which to copy 0x00, and that's it. So this is our assembly line. Load from RAM into register R0 from address 0x00. The next line will be LDR, load from RAM into register, for example, R1, for example, from address 0x04. This is what C programming compiler would generate automatically when you hit compile button. So it assigns addresses for variables, and then it just remembers that a variable A is always address 0, variable number B, just copy paste with number 0x04, for example. A compiler automatically gives these addresses one by one, starting from the lowest. So theoretically, it would put number B in the next address, which would be 0x01. But because we will later expand this example to work on 32-bit numbers, I immediately just put it in location number 4. So next thing is, after we have copied numbers into registers, into CPU, then we need to add them. So I just use instruction add, and then I add these numbers. And as I said, the result will be written into the first of the operands. So for example, I write R0, R1, it means that R0 and R1 are added together, and the result is written back to R0 because this is simple RISC processor. But we don't care that this value is overwritten, because in reality, A is located in random access memory. So if we make a copy of it in registers and then write something over in the registers, it's not a problem because the original value is still in RAM, safely stored and not changed anyway. So we add these numbers together. The next thing that we need to do is store the result into into RAM address number 8. So instruction for that is named str in our case, store. In some programming languages, assemblies is just st, but for our case, we will just use store, str. So register R0 value we want to store into RAM address 0x08. And this is actually the reason why when you create variables in, for example, C programming language or data arrays in C programming language, for example, you write uint 8a, t a is an array of 10 numbers. It would be small t. You cannot later, for example, write that A will be now a different location, like 0x0055, because these things that we define are constant pointers with fixed address. So when we create some variables, their name is actually their location in random access memory. And by convention. So in rare cases, when you only use a variable for a very short period of time in your code, for example, just to loop through, then it is not copied into RAM, it is used in CPU in a register and then just not used again. But in most cases, it is stored in RAM in this manner. So final line is this, and jump end. So after we did our program, we want the program to stop, because as you can see here, for example, in my CPU, I have some code from previous lessons. And whenever we work with microcontrollers, there is this convention that to save flash memory physically, when we write a new code, old code is not deleted, because deleting the code just damages the hard drive, damages the flash memory of the microcontroller. Every time we do some erasing or writing into flash or hard drive or any other permanent storage, it is damaged a little bit, it wears out. So to protect flash memory from wearing out too early, when we program processors, they only delete as much code as necessary to write in the new code. So for example, our code will be 6 lines, so only 6 lines will be deleted and written. And the old code stays in the flash memory, because we don't want to delete and write it every time we touch the flash memory. So this is why the end of code is always appended with this infinite loop, where it jumps to line 5, which says jump to line 5, which says jump to line 5, and so on, so that we don't run into some old code or undefined code inside of our flash memory. So this is why we do this end, jump, end, and all compilers always automatically append this line to our code. In Windows applications, it would actually put code return, because when you open the program, it is like opening a function and then the function returns something. But generally in microcontrollers, it ends with end, jump, end. So now we need to translate this assembly language into machine code. And so the assembly language translates into machine code directly with no secrets or something. So comment in assembly language is started with a semicolon. This is why C programming language lines end with semicolon, but a little bit different meaning. So here, after semicolon, I'll just write how the machine code will look like. So we have instruction load from register, and load from register inside the CPU, it basically determines some part of the machine code. And in our simple example, which is actually very similar to Atmel Arduino processors, load from RAM means that the first 4 bits of the instruction will be 0, 0, 1, 1. And in your head, you already know that in hexadecimal format is 3. So I'll write this machine code in hexadecimal format, because in Logisim, I write it in hex as well. So now I have my assembly code, this document, and I just translate the code. LDR always translates to 3. LDR means 3. So in both lines, I can just immediately write 0x3. Next in LDR is which register number. So in this case, register R0 means there will be 0 in machine code, and register R1 means here will be 1 in machine code. And the next part of LDR is 8-bit address, in our case 8-bit address of random access memory from which we want to read. So it's 2 nibbles, 2 4-bit numbers, so it will be 2 symbols. So address 0 means 0, 0, and address 4 means 0, 4, because it has to be in 8 bits or 2 times 4 bits. So we have generated the first 2 machine code lines. Next operation is add. Add is here, arithmetic logic unit operation. So all arithmetic logic operations start with 0, 0. This tells that it's you have to turn on the arithmetic logic unit. So in hex, it will be beginning with 0. Next, for nibbles is destination register, which is a register R0. So 0 is 0. Next is operation add. Addition is operation number 0. So the third nibble is also 0. And final is source register, or the second register that participates in addition, which is register R1. So here is number 1. So machine code for adding R0 and R1 and writing result into R0 is 0001. And next, store. So we have store instruction here. Its operation code is 0100, which in hexadecimal is 4. Next 4 bits is the register whose contents we want to save. So it's register R0. And finally, store 4 bits is the address in which to store. So address 08. So this instruction translates to 4008, and these bits are not randomly selected. They are just selected through this lookup table here. And finally, end, jump, end. To calculate this, because we can put more lines, I used a label. And the label is just line number. So it basically says to which instruction we want to jump. So line number is 5. So end is 5. So this would actually translate to jump to line 5. The problem is that we write our code in a program that starts numbering from 1, but our CPU program memory starts from 0. So first option would be to subtract from these labels 1. So instead of jump to 5, to instruction 5, we would change it to jump to instruction 4. So this is 0, 1, 2, 3, 4. And this would translate to jump to line 4, jump to line 4, and so forever. But because we will be writing longer codes later, and I don't want to recalculate these locations every time, I will leave it as this, but in the beginning of our program, we will just put one shadow instruction. So all code will start with dummy instruction, which will be, for example, we have this convention that when CPU is started, all registers are set to 0. So basically what we can do is we can just start the code with instruction, for example, load 0 into register R0. So for example, LDI register R0, 0x00, which basically doesn't do anything because it's already 0. But if we just put it in the beginning of our code, and our real code we start to write in program memory starting address 1, 2, 3, 4, 5, 6, and so on, we just don't have to subtract 1 from every label whenever we write it. So this dummy instruction will just be located in address 1, so that we have made a workaround fixing the fact that Notepad++ starts numbering from 1, but we have a program memory starting from 0. So LDI R00 would be translated in the following way. LDI instruction is 0010. So it's 2. 10 is 2. And then register R0 is 0. And the address location, the value is also 0. So register R0 and value 0. So we just take our logsim, and in the 0 address we write 2000, and we just forget about it. And our real code, we start to write from address 1, so that the numbers match. Okay, so now we have written the assembly code. We have translated it into machine code, and now I just have to type in the machine code into Logisim program memory and check out if this code works. To do that, I use this hand tool. I click on the memory location that I want to write, for example, 3000. Oh, it's actually there. Next instruction is, this is all code from previous lesson, so I'll just write over it. Next instruction is 3104. Next instruction is 0001. Next is 4008. And finally, oh, this we didn't translate it. Jump to line number 5 is jump instruction first 4 bits is 0101, which is funny, but it's actually 5. Then next 4 bits are zeros. Next 8 bits are the line number. So line number is 05, is the 5th line, so it's 5. So I write 5005, and that's it. I don't care what's written in the next locations because the program will hang on this line. So I can click reset in my CPU. I can, and then I use my clock here, and I click it rising edge, falling edge. First dummy instruction was performed, nothing really changed inside the CPU. The register content is still 0. Then I do next instruction, clock rising edge. This on rising edge, this instruction is read into CPU. CPU instruction decoder sees that it starts with 3, so it turns on random access memory, selects address number 0, and on a falling edge, it copies the value into a general purpose register. Number 0 is 42 is here. A copy of it is there. On rising edge, next instruction is read. In this case, random access memory address number 4 is selected. And on falling edge, the content is copied into general purpose register number 1. 55 is there. On next, rising edge and falling edge, the numbers are added together. So R0 plus R1 result is overwritten into R0. Let's check out. It should be 97. It is. And on the next rising edge, the next instruction is read, which is write to RAM address number 8. So RAM address number 8 is selected. And on falling edge, register number 0 contents are saved. And as you can see, random access memory location number 8 now has value 97. And next instruction is jump to instruction 5 forever. And I click this clock millions of times, and the program doesn't go anywhere. It just stays in that line. Okay. So if you understood what we did there, please write it in the chat. If you didn't, also raise your concerns. You can write in the chat box if you didn't really understand it, or if you have some questions, please ask them. Okay, somebody says it's clear. Somebody else also says it's clear. So you tried it in your computer and nothing happened in RAM. Did you input the numbers? You need to input the numbers yourself by hand. Let's try it with different numbers. So I input numbers, for example, these are hex numbers. So I'll write A4. And here I will write 1C. Oops, 1C. And in the next location, I write 0, but actually I can leave some wrong number there. When I click reset on CPU, it resets the CPU program counter to line number 0. Let's check it out. First instruction, next, next, next. And the result is overwritten in the random access memory. So let's check it out. A4 plus 1C is C0, and C0 is written there. Are you still having some problems or troubles? Also, there's this button called Clear RAM Contents. So I click it, it just clears the RAM. So I can write something else in A1 plus B2. Now let's check out. I reset the processor. Let's run through this code. Blah, 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 blah. So E1 plus B2 is equal 93. Let's check out E1 plus B2. How do you think will the result be correct? I hit enter and it's not correct. It is missing the top bit because we added two 8-bit numbers, but these numbers were so big, they were bigger than half of the limit of 8-bit number. So we added them together and the result is a 9-bit number. So this is programmer's fault. This is the responsibility of a programmer to define the numbers in such a way that addition, multiplication, bit shifting, and so on does not lose the bits. So if I have a simple counter that just counts from 1 to 100, I can use 8-bit number, like here, unsigned 8-bit type number A and B. But if I'm adding them together and each of them and their sum can be bigger than the 255, then it's my responsibility and duty to define C as, for example, 16-bit number. Okay, so that would be the correct thing. Define C as 16-bit number, and when you do A plus B, the result will be 16 bits. So there's also a little bit asterisk. Well, how does C programming language know that, for example, when it calculates A plus B, how does it know that the result will be 16 bits or not? Actually, there's this little secret. Okay, this is actually a very good idea. So in reality, I don't know if it's the same in web programming languages, but in C programming language, when processor performs these operations, it first automatically upgrades both sides to int, okay? So that when you calculate A plus B and the result overflows, and then it sees, oh, we could write the result in 16 bits, so we do one thing or another. So actually, when you do A plus B or A shifted by B or any other arithmetic operation, actually C compiler upgrades both sides to integer. And then if the resulting register is smaller than integer, then it truncates the top part, the most significant bits, it just throws away, and the bottom part is written into this resulting number. Okay, that's, you know, some information that maybe works for you someday. So we have kind of understood how processor takes numbers from RAM, adds them together, and writes the result back into RAM. And continuing on this carry issue, so let's say we have 8-bit processor, but we want to perform arithmetic on bigger numbers, on 32-bit numbers. Is it possible? Maybe it is, maybe it is not. It would be the same as asking, we have, for example, 32-bit processor, can we run 64-bit operations on it? We have 64-bit processor, can we run 128-bit operations on it? And let's just challenge ourselves and check out if it's possible. So task 2 today is, instead of 8-bit numbers, we need to update our code so that it works on 32-bit numbers. Okay? So unsigned 32-bit integer A is one number, B is another number. As you can see, these are not small numbers, these are big numbers. This is 983 million, 429,781. And the second is also a big number. And we have 8-bit system. Can we work with 32-bit numbers on this 8-bit system? Do you want to try to write an assembly code on your own that performs these operations? So the idea is that now A is located in RAM addresses. Since each address contains only 8 bits, it's an 8-bit RAM, then A is located in RAM addresses from 0x00 to 0x03. So 0, 1, 2, 3, it's located in 4 addresses. The next number, B, is located in RAM addresses 0x04 to 0x07. You know, it's 32 bits, so each of these numbers actually need 4 bytes in random access memory. And finally, C is located in RAM addresses 0x08 to 0x089. 10 is A and 11 is B, so address 0x0B. Okay. Can you do you want to try to write an assembly code yourself which performs these operations? So what you need to do is basically, I'll actually write these example numbers into the RAM so that it's more visual. So I select decimal, I select paste this number. So this is one number, and this will be the second number. They will be written in RAM, and you need to just take them byte by byte, add them together, and write the resulting bytes into the top addresses. Do you have any questions or any clarifications necessary to do this task? You can write it in chat box or ask with your voice. Okay, you actually should have a question, right? And you know, you are computer geeks, so you probably already have this idea in mind. And the question is following. We have, for example, this first number is really good. We have this number, this big number. It is full 4 bytes. This is 1 byte, this is second byte, this is third byte, and this is fourth byte, right? And we need to write it across this random access memory. So the question is, first of all, in what order should we write these 4 bytes into random access memory? Should we start with the top or with the bottom of the number, or maybe differently? So I'll just write 2 options in RAM and you will try to tell me which is the correct. So First option is I write these numbers inside the random access memory as I see them. So top part goes here, so in the beginning of the RAM, so it's 3A. Next part, 9D, goes into the next location, 9D. Next part is F2, so F2. And finally, I write the end of the number 9595. This is option A. Option B is to write the bytes in the reverse order. So this is the smallest, least significant part of the number, just like when we write decimal numbers. So this is 9 billion, and this is just 81. So I would write the bottom part in the lower address and the top part of the number in the higher address. That's the option number 2, and I'll just write it in. So bottom part 95 goes here, 95. Next part F2. Next is 9D, and next is 3A. So please write in chat box, or you can answer with your voice, which ordering of bytes is the correct one, which is correct. Should we first write like this or like this? So which way of writing numbers is correct? In your opinion, you don't have to know it. You can just make an intuitive guess. Just imagine that you have intuition, what your gut says, and just write it in your in the chat box. So Anthony says least significant part with least significant address. Okay. Another person also thinks so. So it's 35 people. So, you know, maybe 10 answers would be good, assuming that, let's say, 3/4 of the classroom are sleeping, but at least 1/4 would write some answer, for example. Okay, 3 people think that the second way is correct. That's good. Any more guesses? We write on the run from right to left. Okay, so it looks like those who think the other way wouldn't even dare to write their opinion, because there's overwhelming opinion that the second way is the correct one. So actually, it turns out that for some historic reasons, both of these methods are actually used, and both of them are at the same time correct and incorrect. So this phenomenon, when you want to store big numbers in small chunks of memory, is called Endianness. There's a Wikipedia article about Endianness, and there are 2 ways to do it: Big Endian and Little Endian. So, and this picture actually shows it very well. So first option is, for example, Big Endian, just like I wrote. So number, this is the least significant part, and on the left is the most significant part. And so we would write it as we see it. Top part is in the lower address, then the next part, and finally in the highest address, the lowest part. And the second option is Little Endian, where bottom part is written in bottom, next is written in the next location, next in the next, and next in the next, and so on, like this. And this Little Endian kind of leaves, at least for me, some intuition that it's a little bit better, because if we upgrade this 32-bit integer to 64 bits, then next bytes will be just written in the next memory locations, and without really changing or modifying the bottom, for example, locations. So Little Endian seems to me to be a little bit better option if we want to, for example, write an array of 8-bit numbers, and then we want to flush them together into 32-bit number or something like that. So for that reason, for me, Little Endian seems like a better option. But unfortunately, in some systems, Little Endian is used, and in some other systems, Big Endian is used. So let's check out. And also there is something called Mixed Endian, but we will not touch it. It's not a good idea. So where is Little Endian and Big Endian used? So for example, there is this IBM System 360 uses Big Endian. Some successor architectures. Then in Unix, let's see, current architectures. Let's just check it out. So in Intel x86 and AMD 64X, blah blah blah. These processors use the Little Endian format. Okay. Also, ARM microcontrollers are all Little Endian. Also, 8-bit AVR processors are Little Endian. But actually, for 8-bit processors, Endianness is determined by the compiler, not by processor. Processor is 8 bits, and it doesn't care in what order we write these numbers and read them. It's just that our compiler needs to do it in the consistent way every time the same order. But actually, 8-bit processors could be used in both Endians, and they wouldn't really care. But in bigger systems, there are some hardware accelerations where you can, for example, faster read if they are in Little Endian format instead of Big Endian. So Big Endian is used in, I think, Macintosh operating systems, but I don't want to like lie to you. And so about Endianness, there was a good article which basically said that Macintosh is considered to be Big Endian, and Linux and Windows is considered to be Little Endian, but you like have to check it. So if you're writing, I don't know, C# applications or web pages, then you don't care because it's taken care of in lower levels of compiler, which programmers don't really access. But if you ever happen to write programs for microcontrollers or programs for in assembly, well, then it's extremely important that you know the endianness of the system. And about the Big Endian, there is this thing called network endianness. Networking. And for some reasons, historically, because people write numbers starting from top and beginning with bottom. For example, let's write how many people live in Latvia. It's 1,900,899, for example. So as you saw, I wrote the number starting from the most significant position. This is why in some systems they have Big Endian, because human writes from the big part to the bottom. And this is probably the reason why networking uses Big Endian, not Little Endian. Most network processors historically have been using big endian, and there's this inertia that let's not make everything worse by mixing everything up. So let's just keep using network endian as big endian. So here you can see that network byte order is like the same as saying big endian byte order. And only in some microcontroller organized protocols like SMB, which is used to communicate between microcontrollers. And since most microcontrollers are little endian, then this protocol is also little endian. But generally network, for example, network protocols, let's say TCP/IP header, TCP/IP packet header. So bytes sent between computers, information is written in bytes, but as you can see, the TCP segment header, for example, when you connect to Facebook or whatever, you are giving source port and destination port. And these both things are bigger than 1 byte. So it's important to know in which order it is. So for example, if you want to connect to port number 1, it's important whether you write 0, 1 or 1 and then 0. And in these, it is written in the order that people would write it. So bottom address would have top part and next address would have bottom part because people read from left to right. So it's easier to read as the stream comes in, right? So in networking, it is big endian. In most computer systems, it is little endian, and yet you need to kind of check it. So long story long, we will make our system little endian just because most of the cases computers are in little endian. Okay, so let's check out. First number is this, so I will write it in little endian. This is the number, and in hex it is, okay, I'll write it as the first number. So 95 is the lower part, is the bottom part. Next part is F2, next is 9D, and next is 3A. And the next location, I'll write the second number, which is this number. So bottom part is A5, next part is E8, next is 5, 4, and finally we append zeros, so 0, 5, like this. So there is a hidden zeros in front of this hex number. So we have written these two numbers in RAM, and now we need to add them using a smaller CPU. How do we do that? Well, just like we would do it with decimal numbers. So we just start with the bottom part, we add it together, then we add the next part together, then the next, and then this final part, and then we just write each sum into the next memory location. Okay, so let's try to write assembly code. We can just write in the same, over the same code. It just, the code will be a little bit longer. So since our CPU has 8 registers, we can just fill the first number into first 4 registers and the second number into the next 4 registers, and then add them together. The result will be overwritten in, for example, the first 4 registers, and then we just send them out to random access memory. So let's just do it. I'll do some copy pasting because I'm lazy. So okay, so we need to do 8 times reading from RAM. We read 8 bytes, 4 bytes one number, 4 bytes the second number. So 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6, 7, 8 readings from RAM. Load from RAM. Then we will just read these numbers, you know, in the order that are written. So register R0, R1, R2, R3, 4, 5, 6, and 7. And memory locations will be also the same order: 0, 1, 2, 3, 4, 5, 6, and 7. And now, basically what this does is registers R0 to R3 contain the first number, and registers R4 to R7 contain the second number. And the order is little endian also. So we can actually just change this machine code immediately also. Load from RAM instruction start with 3. The next 4 bits is the register. So they just go ahead 0, 1, 2, 3, 4, 5, 6, and 7. So updating machine code really easy. And next is the address. So the address go in the same order: 3, 4, 5, 6, and 7. So it loads register R0 to R7 from RAM location 0 to 7. Then we want to add these numbers. So to add them correctly, we need to add register R0 plus register R4, because first 3 registers is first number and the second number starts at register R4. So the assembly code would be like this. Add register R0 plus register R4. Result will be written into register R0. Then we just need to add the next parts: the second part, the third part, and the fourth part. So I just paste 3 more times. Add R0 to R4, R1 to R5, R2 to R6, and R3 to R7, like this. Okay, and let's check it out. We can also immediately translate these instructions into assembly. So add, first nibble is 0, second is first register, next is add is 0, and finally the source register. So this is R0 plus R4, R1 plus R5, R2 plus R6, R3 plus R7. So, this is how easy it is to translate from assembly to machine code. And finally, we want to store the result into random access memory. So result, when we add 2 registers together, to reduce the complexity, all RISC microcontrollers have this thing that result is written back into the first argument. So result is in registers R0 to R3. So we just need to store R0 to memory location number 8, R1 into memory location number 9, R2 in memory location number 10, but 10 in hexadecimal is A, and register number R3 to memory location number B, and actually translates to assembly to machine code, really simply, like this. So store is instruction 08, and here is 0, 1, 2, and 3. So store instruction str is right here. It begins with 4, then is register number, and then memory address. So 0, 1, 2, and 3. register RAM address 8, 9, A, and B. And now finally, end, jump, end. So now end is located in address number 17. So it will actually translate into jump to line number 17. And we just need to translate 17 to hex. Can you do it in your head? 16 is 10, 17 is 11. So I write 17 and the result is hex 11. So here it should be 11. 0x5 means it's a jump instruction, then unused for bit 0, and then address to which to jump in flash memory, address number 17, so it just jumps to itself all the time. So since we have more instructions than fits in this window, in a Logisim, I click on program memory, I right click and I click edit content. And now I just need to write this assembly, this machine code into this hex editor flash program memory. Okay, let's go. It is, the first instruction is this dummy 2000. So I leave it there. The next is 3000 is okay. Next is 3101. Then is 3202, 3303. Next is 3404, 3505, 3606, 3707. Okay, so first part is just copying 8 times from random access memory. Next instruction is 0004, so we add bottom parts. Next instruction is 0105. Next instruction is 0206. We add register R2 and R6 together. 0307. And then is store instruction. 4008 means store register number 0 address 8. 4109, 420A, 430B, and jump is 5011. Okay, let's check out if we calculate everything correctly. I click reset, and reset button on computers only clears CPU and program memory jumps to beginning. Random access memory is not cleared by reset button on computers. It can hold some random values inside. So we input these numbers. Let's just check out if it works correctly. So first thing is read numbers. As you can see, random access memory is read one by one. And if I go into CPU, general purpose register, the numbers are copied into registers byte by byte. Next is addition. When we add two numbers, register R0 and R5 are added together and result is written to R0. Next additions add the next parts. And then for times we store the byte by byte result into random access memory. So here, and finally it's jump to end. I can click this clock, it's not moving ahead. So let's check out if the result is correct. So first number, also you can write in the chat box, do you think the result will be correct or incorrect? And have you already spotted a mistake if there is any? 5 seconds to write in the chat box if the result will be correct. So let's check out. the numbers, the results. So result is 1A, that is correct. And the next part, DB, but we have DA, so it's not correct. Next part is F2, but we have F1, so that is also incorrect. Top part is 3F, that is correct. Can you tell me what the problem is, why the result is wrong? Exactly. You are absolutely correct. When we add the first part, 9, 5 plus 8, 5, 9, 5 plus 8, 5, the result is actually a 9-bit number. We have this carry that we also need to add to next position addition. So absolutely correct. You're writing the correct answer here. So when we add the bottom parts, we want carry to be forced equal to 0 because we don't want to add extra carry from some previous operations. So initially we use instruction add, which is right here, add. It forces carry to be 0. But then for the next positions, we want to use instruction add with carry because after addition, if there is an overflow, if there is a carry 9-bit, it is stored in status register. And if we use instruction add with carry, then the carry is read from status register and added to next position pair. And if there is a carry there, it is stored then in status register and so on. So instead of add, first time we need to use add, but in the next 3 times we need to use add with carry. Add with carry, add with carry, and add with carry. And add with carry is the same as add, but just the third nibble is changed from 0 to 1. So here we just change to 1 in 3 places. Add with carry is, for example, register R3 and R7, arithmetic logic unit operation 0, register 3, operation is add with carry, it's number 1, and register R7. So this might be a little bit tricky. Why are all arithmetic logic unit instructions starting with 0 if we're doing instruction number 1? Because these are sub instructions of this big arithmetic logic unit instruction. So these zeros turn on arithmetic logic unit, and these just select which operation in arithmetic logic unit we want to perform. So now I go into this flash memory, I edit contents, and for 0, 0, 0 remains the same. Add R0, R4, and force carry to be 0 as input. And if there's overflow, it will be stored in status register. And in next positions, I change them from previous value to 0, 1, 1, 5, which is add with carry. Instead of 0, 2, 0, 6, I change to 0, 2, 1, 6. Next is 0, 3, 1, 7. And if I do this and I reset the processor, and if I run the code again, it reads the first number, the second number, it adds them together, and then it starts to write the result into RAM. So 1A is correct. And the next part is changed to DB because previous one had overflow, so it's added to DA, and it is DB. Next part changed to F2, and the final part didn't change because that one didn't have carry, so it was accidentally correct. Okay, so now once more, if I copy first number plus the second number, then the result is in hex 3F F2 DB1A. So now the result is correct. Okay, so did you understand everything that I tried to explain? So, okay, that is great. So in most systems nowadays, if you write in C programming language int, it is actually int 32 T. It is usually 32-bit number. This is true for ARM processors, for Windows, for, I don't know, maybe Linux also uses 32-bit numbers as integers. So basically, it's programmers' responsibility to select the sizes of numbers such that the result will fit the resulting number. So if we, for example, have overflow even after top byte addition, well, then it was our mistake that we defined C as 32 bits. If we think that A and B can be so big that the result will be 64 bigger than 32 bits, then it's our responsibility to write that C is unsigned integer 64-bit. Okay. So most systems have 64-bit integers defined. Some of them maybe also have unsigned integer 128T, just without this underscore. But you need to be careful because there is one case where in one microcontroller's one compiler, this thing, unsigned 64-bit integer, was actually defined as it was defined as 0.3dv array of two 32-bit numbers. I don't exactly, oh no, it was hashtag define. It wasn't even, you can't really even do this with type defs. It was something like define OIN64T as OIN32 of X as an array. And this is absolutely criminally wrong way to do it. But in that particular system, the compiler creators were, I don't know, maybe lazy or something, or they just didn't think that anyone would use 64-bit numbers on a 8-bit processor. So they defined 64-bit numbers like this. And if you try to do some arithmetics on an array, it will just give you compile errors and will not work. So just in case you use 8-bit processors or any other processor, it's best to just check out if these 64 and 128-bit numbers are really defined, and maybe they aren't. Okay, Simplicity Studio. So that's just fun fact. So in 32-bit systems, operations on 64 bits are done exactly the way that we did here. So first 8 bytes are copied, then the next first 4 bytes are copied, then the next 4 bytes. Then these numbers are added together and results are stored there, like in pieces. And just for your knowledge, practically always random access memory is organized in bytes, because many times you have simple small counters that count from 1 to 100. It's sufficient to just use 1 byte in random access memory instead of 4 bytes for a small number. So oftentimes numbers are really stored just 1 byte. But for systems that use, for example, 16 or 32-bit numbers in CPU, there is this that I told you, I think, already before. Random access memory has this acceleration where it can read 1 byte or 2 bytes or 4 bytes. This data lane is actually 4 bytes wide, but the restriction is that the address needs to start with a number that divides by 0 or by 4 for 32-bit numbers, or sorry, not by 0. If you read 2-byte number, then the address needs to divide by 2, and if 4-bit number, then it needs to start with a number that divides by 4. It can read 4 bytes at the same time, but only from if they are aligned by 4. Okay, let's check out. For example, here is Simplicity Studio, a place where you can write code for Simplicity Studio ARM processors. And let's just check out if they have a type of uint64t. Let's see if we have that. In these Eclipse environments, when you control click on some object, it brings you to the definition of the thing. Let's see. And let's check out if it's defined. Unfortunately, oftentimes these codes are generated by computers, so you just need to keep clicking somewhere, type def blah, blah, blah. And where's the definition? Okay, now it's hard for me to show you what the definition of this thing is. Default types std int. This is just declarations. Okay, these are stupid files. I think that these things are defined in file called int types. Int types.h. Oops. Int types blah blah blah. Okay, in olden days, when I started programming, there was this file which just had the integer types defined, and you could see if it is defined and how exactly it is defined. Unfortunately, in modern days, it's just so hidden that, you know, I can control click on these things and it doesn't take me to the place that I want it to take me. But it is possible that blah, blah, blah. Okay, that's stupid. Okay. So in olden days, it would write this following thing. Type def uint32t as, for example, unsigned long int. That would be a type definition of unsigned 32-bit number. or the opposite way. Wait a minute. Nowadays it's so hidden everywhere that it's impossible to show you. So let's say, do we have unsigned 128-bit number? So as you can see, unsigned 128-bit number is not defined. So on these ARM 32-bit processors using this particular compiler, we cannot use 128-bit numbers. I know that we can use 64-bit numbers, but 128-bit numbers are just not defined. However, it's determined by the compiler, because if you really think about it, of course, the compiler could support 128-bit numbers. It's just that it would need to load the numbers 4 times instead of 2 times, right? So actually these CPUs are universal, and they theoretically could support numbers with hundreds of bytes or thousands of bytes. There's no physical limitation for a processor where it says, okay, I cannot deal with more than 64 bits. Since these numbers are divided in chunks, and also you can do addition and subtraction on chunks of these numbers. So theoretically, these numbers could be 128-bit, 256-bit, and so on. It's just that compiler creators stopped at 64-bit. And that's their decision, basically. Okay, so I guess that's all for today. We don't really have more time to talk today. So if you have some questions, you can ask them in the chat box. Otherwise, I think the lesson can be ended. Okay, so, oops. Okay, so if no more questions, then we can just finish the lesson. And tomorrow you will have lab. Last week, by the way, Ortus was kind of down, so I couldn't even upload the lab. So if you didn't do it last week, then you can do it this week. I could upload the lab later that day, sometime in the evening. So you can do the lab tomorrow, even if you didn't do it last week. So yeah, the lab is available.